2.8, we're going to talk about something called systems of linear equations. And a system of linear equations is really two or more linear equations that have the same x and y coordinate point that will satisfy both equations. Or when you substitute the coordinate point xy, it will make both of the equations true. Okay? So let's see this once. Whoops, I think I went 2 pages there. Oh, more than 2 pages. My goodness, one more time. Okay. So, for example 1, if we're going to solve a system of linear equations, and these are the two that were on the first intro to the lesson, we have y equals 2x minus 4, and we have y equals negative 3x plus 1. So the first way we're going to see the solution to the equation is by graphing the equations. So if I'm going to graph the first equation in blue, I'm going to, let's see if I can get my point here. I'm going to go to, first of all, to the beginning, my y-intercept. And sorry, I'm doing this with my finger, so I'm trying to see where I have that. It's not working with my stylus very well. Let me see if I can get that to negative 4. Well, I'm making it larger, aren't I? Okay, well, it's on negative 4. It's just very, very large. And then we're going to apply the slope, which is, oops, one last thing. Let's go ahead and label this. So this point, this very large point, is my y-intercept, which is at 0, negative 4. And now I'm going to apply my slope. Yeah, I just can't seem to grab my clone when I'm doing it on the iPad. Let me see if I can grab it on the computer itself. Oh, kind of having problems there too. There we go. Okay, now that I have it out, maybe I can get it with my stylus. Nope, still can't. All right, I want to go up to and over 1. Yeah, I'm going to have to do this with the laptop. Just 1 minute. Do a little rearranging here of my materials. Okay, so actually then I'm going to get rid of this kind of obnoxious one here. Let's put our first one at -0, negative 4, which is my y-intercept right here. And now I'm going to apply this slope, which is 2 over 1. Again, that's just being a bugger. So we're going to go up 2 and over 1 because that's a positive slope. And see if I have any better. And I'm going to go ahead and put this line through my points. There we go. That worked a little bit better. Working right on the computer instead. All right, now I'm going to go ahead and I'm going to graph the bright green one. So I'm going to go to the beginning again, and this time my y-intercept is going to be at 1. Oh, did I forget one thing again? I did. And this part's a little easier. I'm going back and forth, excuse me, between the iPad and the laptop. I forgot to label my slope here. So my slope ended up being at 1, negative 2. All right, and I'll label my green point here while I have my stylus. So that's going to be at 0, 1 because it is a y-intercept. And then I will go ahead and go back to my laptop and apply the slope. Let me get my clone point here. So the slope this time is going to be go down 3, 1, 2, 3, and over 1. And see, that's also going to be at the point 1, negative 2. So now I'm going to apply my line here. Scoot it over. And you can see that when we have a system, we have an intersecting point, and that intersecting point happens to be at 1, -2. Now, we think that 1, -2 is the solution of the system, but just to make sure, we're going to check that algebraically. And the way we're going to do that is the way we've done before. We are going to go ahead and substitute this in. 1 would be my x, so that would make, let me undo that, that's too hard to read. Let's try it one more time here. That would be 2. Oh, I'm a little bit, this is just not working for us tonight. 2, come on, try it again. 2 times, I'm going to substitute in, to make my 2 a little uglier, my x coordinate point, which is 1, minus 4, and that is supposed to be equal to my y value, which is -2. Let's see if that's a true statement. 2 minus 4, 2 minus 4 is -2, and that makes that a true statement, -2. Now, for it to be the solution to the system, that same point, 1, -2, needs to also satisfy the green equation. So let's try it here. So substitute in y, which is -2, equals 3 times my x value, which is 1, so -3. It doesn't look much like a -3. It's -3 plus 1. So I'll go ahead, I'll multiply it out. Maybe that the next -3 will look a little easier. There we go, -3 plus 1. -3 plus 1 is -2. So I have -2 equals -2. So you can see that is also a true statement. That's what it means to have a solution to a system. So, going back a moment, you can see that we can graph it. If we can go ahead and graph it, we can find an intersecting point. When we find that intersecting point, then we can go ahead and we should always try to check it algebraically and make sure that truly is the solution to that system of equations. So there can also be some systems that have no solution or have many solutions. So the one that we just checked was when there is an intersecting point, and when there is an intersecting point, that means there is one solution. Now we're going to check on the no solution and infinitely many, and you can just write many or no when you're doing these types of problems. So we're going to start out again with graphing first. So let me change positions here again. Let's graph the blue one first. So when I'm graphing that equation, I'm going to go ahead and I notice that I'm going to start with my y-intercept, which is at 1. I'm going to label them after I put the points in there just to make things a little easier on me switching tools and computers and things. And now I'm going to go ahead and I'm going to graph my slope, -2. So I went down 2 and to the right 1. Remember, you could also, while I'm here, I'll go ahead and show you this. I could go up 2, but then I need to make the negative to the left. And then I would go ahead and plot my line. Whoops. There we go. Let's see if I got that about right. Almost, a little off there. Move this one over a little too. All right, so that is the blue equation. So let me go ahead and label my points there. So our first point was our y-intercept, and that was at 0, 1. My next point, I applied the slope going down 2 over 1, and then if I label that, it would be 1 for the x and -1 for the y. And then I showed you could also do that in the opposite way for it still is, notice it still is a negative slope, and our point over here would be going over -1 and up 3. Okay, a little delay on my writing, but I guess you can read that. Okay, going back to, let's go ahead and graph the green line. So the green line again, start at my y-intercept, and that's going to be at 5, 0, 5. Start at the beginning. And now I'm going to apply my slope. So my slope this time, again a negative slope. I'm going to go down 2 and over 1. And since I did it with the blue, I'll do it here too. Up 2 and over 1 to the left. And let's get our line in there. All right. And I'll try to label at least some of those points here. Get my greens. There we go. So when I went to my y-intercept was at 0, 5. My applied negative slope when I went down 2 would be at 1, 3. When I went up 2 and over to the left one would be -1, 7. Now remember, I would like you to plot and label 2 points when you're doing lines. Now you're going to notice that when we graph these two systems, or this system of 2 equations, that these lines are exactly parallel. The lines are parallel, so they will never intersect, so they will never share an xy coordinate point. They're never ever going to cross. Now, without graphing this, I could notice this because I can see here that my lines have the same slope, but each line has a different y-intercept. So that will also tell me these are parallel lines. That means there is no solution for this system of equations. This time we have 2, and these are my beginning equations. We have the blue equation that starts out 2x minus y equals -3. And we have the green equation, -4x plus 2y equals 6. Now again, I could go ahead and graph them first to see if I have no solutions, or many solutions, or one intersecting point that would mean one solution. So to graph, whenever I see the word graph, I will know that I need to put in slope-intercept form. So you can see I did that. I moved my 2x, added 2x to both sides, and then I went ahead and I had a negative y, so I multiplied everything by a negative. After doing so, I have the blue equation in slope-intercept form, so it's ready to be graphed. Start with the y-intercept at 0, 3, and then I'm going to go ahead and apply my slope up 2 over 1. While I'm moving things, I'll move the line into there, and then I'll do some um, labeling of my points, just because of, let me see if I can approximate that slope. Move that over. Oh, that was pretty good. Okay, so now I need to make sure that I'm labeling my points. So I have the y-intercept at 0, 3. And I have the applied slope of up to over 1. So I need to look at my x, which is 1, and my y, which is 5. Okay? You can see I did the same thing with the next equation, the green equation. I went ahead and I isolated the y. First it was 2y equals 4x plus 6. And then I needed to divide everything by 2 because I needed to solve for a single y. Now I can go ahead and graph that by using the y-intercept, which is 3 again. I'm going to do one thing here first. Just make this a little easier for you. Maybe. Maybe it's not going to be easier for you. Let me shift my tools around here a little bit again. I'm going to move my, here we go. I'm going to make my green, or my blue points a little bit larger. So this is at 0, 3, and this is at 1, 5. And then go ahead and put that through there again. Okay, now I'm going to place my y-intercept at 0, 3. You can see why I blew that up a little. It is the same y-intercept as the other equation. Now I'm going to apply my slope, which is up to over 1. And again, I am in the exact same location. So that means that those two equations, even though they started out very differently, when put into slope-intercept form, turn out to be the same equations. That means that there are many, all of the x and y's on those lines are solutions. And since it's the same line, that means there's infinitely many. Again, if I didn't go as far as graphing these, but I put them in slope-intercept form, I can see their slope is the same. So that means they're going to be angled at the same way, if you'd like to say it that way. But then I also notice this time they have the same y-intercept. That means that the slope of the line is the same, but it is also crossing the y-axis at the exact same point. So that means it's the same line. So that would mean there are many, infinitely many, every xy coordinate point on this line will satisfy both of those equations or be a solution to the system. Now, our next one, I think you should do pretty good with because many of your 10 marks questions were similar to this. So, a company offers 2 plans for high-speed internet. Plan A, you have to pay $200 for the modem and then $30 per month for service. For Plan B, the modem is free and you pay $40 per month. What we want to know is, after how many months are the total cost of the plans the same, and when is A a better deal and when is B a better deal? So first of all, we need to put this information into an equation, a linear equation. So with Plan A, you pay $200. That's a constant term, and we talked about our constant term being our y-intercept. Now, you also pay a per month for the service. When we see that word per, we know that's going to be a rate of change or our slope. So that information is going to go as the coefficient to x. Now Plan B is a little bit different because the modem is free. We do not have a constant all the time charge. We only have our per month charge. So there is no slope to Plan B. I'm sorry, there is no constant term to Plan B. See, there's nothing there. But we still have to put in our rate of change, which is 40 over 1 or 40x, because we need to have the per month is the rate of change. Okay? Now, it told me that we want to know when are the costs the same. So I'm going to take the two equations I just made, They both were equal to y. I want to see when those y's are exactly the same. So I'm going to set those two equations equal to each other. So the 30x plus 200 and the 40x, and there was no constant term. Now I'm going to erase those last lines that I made just so that I can show you the solving here, because it's not showing it on the typed one. Now, to solve this equation, I'm going to get my like terms together. So I'm going to go ahead and I'm going to subtract 30x from both sides. This time the constant terms are going to be on the left side and the variables on the right. Then here we would need to divide by 10, and you'll see then we get 20 equals x, or when they'll be the same is after 20 months. Okay, and how much they would cost is going to be $800 because we're going to put the months in there. So 30 times 20 is 600 plus 200 would equal 800. And in Plan B, 40 times 20 would also equal 800. Now the last part of the question, whoops, I think it went twice, and a little bit of a delay here. I think we have one more. Oh, I guess we don't have a screen. I guess we finished it with how much would it be, and it'll be $800. And that concludes lesson 8.8 about linear systems.